Bismillah ar-Rahman ar-Rahim. We are interested in this integral involving the hyperbolic sine and the gamma functions. The integral is parameterized by the positive integer n. We are interested in obtaining the value of this integral as a function of n. Let's start by representing the hyperbolic sine and gamma functions using their product representations. The hyperbolic sine of pi x is equal to pi x, the product k from 1 to infinity, 1 plus x squared over k squared. This means that x over the hyperbolic sine of pi x is 1 over pi, the product of the reciprocal of this quantity, which is k squared divided by k squared plus x squared. The reciprocal of gamma of y is y e to the small gamma y, that's the Euler-Mascheroni constant. Then we have a product k from 1 to infinity, e to the minus y over k times 1 plus yk. If we apply this to this part here in the integrand, we have n+1 plus ix, we have n+1 minus ix. Together, these give us n+1 squared plus x squared. Then we have e to the power, the Euler constant, and the sum of these two guys, which is 2 times n+1. The exponential inside the product will be e to the minus 2 over k times n+1. Then we have the product of these two brackets, 1 plus n+1 plus ix over k, 1 plus n+1 minus x over k. These two can be written as 1 plus n+1 over k plus I x over k times its complex conjugate. This product is 1 plus n+1 over k all squared plus x squared over k squared. In this product, I multiply and divide by 1 plus n+1 over k squared. Afterwards, the product is split into two products. In one of them, we have this bracket divided by that bracket. The exponential and the square are in this product here. Also, this bracket is multiplied and divided by n+1 squared. Here is n+1 squared, and then we have this ratio of n+1 squared plus x squared over n+1 squared. This is the integrand. X over the hyperbolic sine of pi x is 1 over pi, and then we have the product. This is pi, and this is the product coming from this term here. I write down this product in the denominator after multiplying upstairs and downstairs by k squared. This ratio is here. What about this bracket? This bracket is the square of n+1 e to the gamma n+1 product k from 1 to infinity, 1 plus n+1 over k times e to the minus n+1 over k. What we have here is exactly 1 over gamma n+1. Then we square. Gamma n+1 is the factorial of n. Let's look carefully at these two products. The product in the numerator is 1 squared over 1 squared plus x squared times 2 squared over 2 squared plus x squared. Then we have n squared over n squared plus x squared, n+1 squared over n+1 squared plus x squared, n+2 squared over n+2 squared plus x squared, and so on. In the denominator, if k is equal to 1, then what we have is n+2 squared over n+2 squared over x squared, which is like this term here. We can see that the subsequent terms will cancel the subsequent terms coming from this product in the numerator. The ratio of these two infinite products is this finite product. We also have this ratio here. This one together with this have a product of 1. We are left with the product k from 1 to n, k squared over k squared plus x squared. Our integral is 1 over pi factorial n squared, integral from 0 to infinity, this product here. Since we are integrating a product, it may be a good idea that we do partial fractions. The mth term here is 1 over x squared plus m squared, which is 1 over x plus im times x minus im. We try to write this product as a over x minus im plus b over x plus im. In other words, we can write down this product as the sum of 2n terms. Each one involves a symbol ball. How can we obtain the coefficient a? We can multiply the left and right hand sides by x minus im, and then take the limit as x tends to im. When we do this, we get a on the right hand side. On the left hand side, we get the product. But when it comes to the nth term, after multiplying by x minus im, we are left with x plus im. Now we put x equal to im. What we get from here, 1 over 2 im, and from there we get the product, im plus ik times im minus ik, and there is a product here, k not equal to m. These two brackets together give us minus n squared plus k squared. So a is equal to 1 over 2 im, the product, k from 1 to n, k not equal to m, of 1 over k squared minus m squared. To get the coefficient b, we multiply both sides by x plus im. Then we take the limit as x tends to minus im. On the right hand side, we get b. On the left hand side, we get this product, excluding the bracket x plus im, and then x is replaced by minus im. We obtain that b is equal to minus a. Rather than writing the product as the sum of two n terms, we can sum the pairs. This pair gives us x squared plus m squared downstairs, and upstairs we have a times x plus im plus b, which is minus a, then x minus im. The numerator is 2ima. The product that we are interested in integrating is that of k squared over x squared plus k squared, k from 1 to n. Applying the product to the numerator, we get 1 times 2 times 3 all the way to n all squared. That's the factorial of m squared. Then this product here can be written using partial fractions. It will be a sum with n terms. Each term is 1 over x squared plus m squared. Then there is a coefficient which is 2ima. 2im times a is this product here. Writing this product using index j, we have product j from 1 to n, j not equal to m, 1 over j squared minus m squared, which can be written as j minus m times j plus m. We need to integrate this sum with respect to x from 0 to infinity. This integral is 1 over m tan inverse x over m. When x is 0, this is 0. When x tends to infinity, the arctangent function tends to pi over 2. When we do the integration, we get pi over 2m. Now our integral is converted into a sum with n terms. So far, we rewrote the integral as 1 over pi n factorial squared, then a product. Applying the product to k squared gives us n factorial squared that will cancel this n factorial squared. We rewrote this product as a summation. Then we integrated term by term. After integration, this became pi over 2m. This pi goes away with that pi. This 2 is here. Now we have a summation m from 1 to n, 1 over m, and then this product here, which can be written as a product with 1 over j plus m, and another one with 1 over j minus m. And this product here can itself be split into two products. In one product, j goes from 1 to m minus 1, and in the other, j is from m plus 1 to n. Can we obtain this summation in closed form? Let's try to express each product using factorials. If we start with this one, when j is equal to m plus 1, we have m plus 1 minus m. That's 1 over 1. When j is m plus 2, we get 1 over 2. When j is equal to n, we get 1 over n minus m. This product here is 1 over n minus m factorial. For this one, when j is 1, we have 1 minus m. When j is 2, we have 2 minus m. When j is m minus 1, we have m minus 1 minus m. We have m minus 1 terms. Multiply each term by minus 1. So we have in the numerator minus 1 to the power m minus 1. In the denominator, we will get m minus 1 times m minus 2 all the way to 1. This is the factorial of m minus 1. Finally, this product is missing the term when j is equal to m. Let's make the product from 1 to n with all the terms, but then we get an extra term, which is 1 over 2m. To compensate for that term, we multiply by 2m. And what is this product? It is 1 over m plus 1, 1 over m plus 2, all the way to 1 over m plus n. This bracket here is the factorial of m divided by the factorial of m plus n. Therefore, this product is 2m m factorial over n plus m factorial. This one is minus 1 to the m minus 1 over m minus 1 factorial. And this one is 1 over n minus m factorial. This m goes away with that m. We have 2 that cancels this 1/2. M factorial divided by m minus 1 factorial. That's m. Then we have n plus m factorial, n minus m factorial. We multiply and divide by the factorial of 2n. This is the binomial coefficient. 2n choose n minus m. The summand now is this minus 1 to the power m minus 1 times m times this binomial coefficient. If we get this sum in closed form, we are done. One way to obtain this sum is to use the integral representation of the binomial coefficient. The binomial coefficient v choose k can be written as 1 over 2 pi I, then a contour integral about the origin. The integrand is 1 plus z to the power v divided by z to the power k plus 1. Applying this to our case, the binomial coefficient 2n choose n minus m is 1 over 2 pi I. Then we have our contour integral. We can just think of integrating along a circle with radius that is between 0 and 1. The integrand has a numerator that is 1 plus z to the power 2n. In the denominator, we have z to the power this quantity plus 1. We have z to the n minus m plus 1. Swapping the order of sum and integral, we are summing m from 1 to n minus 1 to the power m minus 1 times m times z to the power m minus 1. Obtained from this guy here, because 1 over z to the n minus m plus 1 is z to the m minus 1 divided by z to the power n. This summation can be written as minus the derivative with respect to z of the summation m from 1 to n minus z to the power m. If we differentiate, we will get this m here. The power will be m minus 1. The summation is now a geometric series, which gives us this function of z. Finally, we differentiate with respect to z. This quantity here is this summation. We are not done yet. We need to take this function of z multiplied by 1 plus z to the power 2n divided by z to the n, and then integrate. If this z to the power n is eliminated, then we have no poles inside the contour of integration. Our function is analytic, and the integral is exactly equal to 0. When we divide this result by z to the power n, this term, and that term give us a function with no poles, and the integral is equal to 0. In other words, what is really important in evaluating this integral is this minus 1 here, which is 1 when we account for this minus 1 there. The sum of interest is 1 over 2 pi I, and then the integral 1 plus z to the power 2n minus 2. This minus 2 is because of this 1 plus z squared in the denominator. Note that this power here is always greater than or equal to 0 because n is greater than or equal to 1. And then we have z to the n in the denominator, indicating that we have a pole of order n at the origin of the z-plane. By the residue theorem, this is 2 pi I, which will cancel with this 2 pi I. And then we need the residue of the pole of order n at the origin. This is 1 over n minus 1 factorial. Then the limit as z tends to 0. The derivative of order n minus 1 of this integrand after multiplying it by z to the power n. So we have here 1 plus z to the power 2n minus 2. If we differentiate once, we get 2n minus 2, 1 plus z to the power 2n minus 3. If we differentiate twice, we get 2n minus 2 times 2n minus 1 plus 1 plus z to the power 2n minus 4, and so on. When we differentiate once, we get 2n minus 2, which can be thought of as 2n minus 2 factorial divided by 2n minus 3 factorial. When we differentiate twice, we get 2n minus 2, 2n minus 1, and this is 2n minus 2 factorial divided by 2n minus 4 factorial, and so forth. We need to differentiate n minus 1 times. When we differentiate once, we subtract 3, twice we subtract 4. So our result here is 2n minus 2 factorial divided by 2n minus, between brackets, 2 plus n minus 1, that's n plus 1. When z tends to 0, the bracket tends to 1. So our result is 2n minus 2 factorial divided by n minus 1 factorial, and then there is this n minus 1 factorial here. We can multiply the numerator and denominator by 2n minus 1. We get 2n factorial upstairs. Downstairs, we have 2n minus 1. N times n minus 1 factorial, that's n factorial. We still have n minus 1 factorial. We can multiply the numerator by n and have this n factorial squared in the denominator. This is our summation omega. Our integral of interest is this summation divided by 2n factorial. So our final result is this without the 2n factorial. This integral is equal to n over 2 times n factorial squared times 2n minus 1.